All right, everybody, welcome back. And today we're going to finish up the PM Notes, which is talking about probability models. Basically, last chapter we found specific answers. In this chapter, we're looking at if there is a pattern with those answers. So if you'll turn with me to question number 7. This is actually a fairly interesting question, and it'll be a surprising answer in the end. It says, if you have 30 unrelated people in a room, what's the probability that at least 2 have matching birthdays? My biggest classes have about 28 kids in them. You would think that the odds wouldn't be that high that 2 people in that classroom would share a birthday. So in order to solve this, we're going to first need to answer the complementary question. That means kind of the opposite idea. What's the probability that no 2 people in the room have matching birthdays? So what's the likelihood that they all have different, unique days? So let's start off with a simple idea of just 2 people in a room and then gradually work our way up towards the 30 people that the question is asking us for. So 2 people. If I am in a room with 2 people, I want to know what the probability is that they will have different birthdays. So what's the probability that they are different? So if you think about the first person that you would maybe ask, they would have a total of 365 days to choose from. So they're unrestricted. They can choose any day they want. They can be born on any day. There's no restriction. 365 out of 365. But if I am having a second person and I want them to all have different birthdays, that means they can't choose any day they want. There's one specific day from this first person that they are not allowed to choose. So they have 364 days out of 365. Now if I multiply those 2 things together, I get the odds that they will have different birthdays. So multiplying those in your calculator, you get 0.997. That is a 99.7% chance they will have different birthdays. So what if we started to scale this up? What if we went from 2 people to maybe 3 people? Well, doing that would have this same fraction, but then it would add a third fraction. As you can probably see, there's a pattern to those numbers. It goes 365, 364, 363 days that they are allowed to choose from. So if we take this and we go to 30 people now, so this is how big our classroom is, the probability that they would have different birthdays would be 365 out of 365. That's the number of days they could choose. 364 out of 365. 363 out of 365. And it continues until we get to the last person. So this is the first person, the second person, the third person, so on and so forth, until we get to the 30th person. And they would have the fraction of 336 out of 365. So you would think maybe you would subtract 30 from this first number. You can't subtract 30 because you have to count this first number. So in reality, you're just subtracting 29. If we multiply all of those up, we are going to get 0.294. Now that's the chance that they're going to have different birthdays. If you remember back in our original question, they are not asking for the chance that they will have different birthdays. They're asking for the chance that they will have matching birthdays. That means they'll be on the same day. But we know if they have different birthdays, the opposite of that would mean that somebody matches. We don't know exactly who would match, but somebody in the room would match. So for example, with the 2 people up here, I know it's 99.7% chance likely that they will have different birthdays, but if I take 1 minus that 99.7, that's the likelihood that those 2 people, if they were the only 2 people, would have the same birthday. And it's 0.03% chance. Not very likely that 2 people in a room, if they just met, they would have the same birthday. 30 people, you can see that that's going to change a little bit. We have 1 minus the number that we got at the end, which is 0.294. And if we take and subtract those, we get a 70.6% chance that 2 people out of 30 might have the same birthday. It's kind of fun because you can ask around the room and see, hey, who might have the same birthday. And this sometimes plays out in classes in the past that I've had. There have been people who've had the same birthday and they didn't even know it. The odds are slightly higher than you would think. This is a really cool problem that probability models can be used for. And this idea of kind of multiplying by numbers, and some go up, some go down, that's kind of what we're going to be going towards with our second target. Let's go ahead and let's flip to question number 8. A study of education followed a large group of 5th grade children to see how many years of school they eventually completed. So let X be the highest year of school that a randomly chosen 5th grader completes. Students who go on to college are included with the outcome of X equals 12, so they didn't actually count those college years. It's just that you finished high school, you finished 12 years of school. The study found that this probability distribution for X, our random variable, has these numbers associated with this table. Is this a legitimate probability distribution? Well, how do we know that? We know that it's legitimate if the probabilities all add up to be 100%, which in this case should be 1. If we take all those decimals and we add them up, I believe we do add to 1. So we know it's legitimate because all of the probabilities add up to 100%. Go ahead and take a second. You can copy that down. So let's look at B. What percent of 5th graders eventually finished 12th grade? So we're looking specifically here at the probability of them going through 12th grade. So if we look at this diagram, we have to kind of understand what it's saying. If we look, 4 right up here means they completed 4th grade, but they did not complete 5th grade. 4th grade is the last year of school that they finished. 5 means they completed that year of 5th grade, but they didn't go on to 6th grade, or they didn't finish, or they dropped out, or whatever. So here, when I'm looking at 12, what is the P of 12 specifically? That is going to be 0.752. How many people completed 12th grade? All of these people did not complete 12th grade. We can't include them. We aren't interested in less than 12th grade. We are interested only in 12th grade itself. So that is 75.2% of 5th graders eventually finished 12th grade. I'm just going to abbreviate. You're more than welcome to do that too. Underline what you're looking for and then just put a little arrow. So with part C here, we start to move on to a different idea where we're including multiple things. Find the probability of X being greater than 6. So X being the highest year of school that they completed. So let's see. Probability of X being greater than or equal to 6. That could be any of these. That could be any of these values. So I'm going to need to add them up. Notice how I included 6 in here because there's that equals to sign. If I sum those on my calculator, I will get 0.983. There's another way that you can get this pretty simply. Because we know the whole thing's 1, we can subtract those two things that are left over. So if I subtract 0.010 and 0.007, I will get this answer. So again, that is 98.3%. The idea that's behind that, 98.3% of students finish 6th grade or higher. Now, if you're doing a report on schools, that would be a good thing. If 98.3% of students are finished 6th grade or higher, that means they are continuing on in their education. So what about D? Probability that X is just greater than 6. Notice C and D look very similar, except that with this one we cannot include 6. There's not the equals to underneath that inequality. So that means it has to be 7 through 12. So if I go ahead and add those numbers up, or if I just subtract another 0.007 from my previous answer, I will get 0.976. That stands for 97.6% of students finish 7th grade or higher. So let's look at the last couple of questions with this. E, what values of X make up the event the student completed at least 1 year of high school? High school, remember, begins with 9th grade. So what's the probability of that event as well? If I'm going to write this in symbol notation, that would be the probability of X being greater than or equal to 9. If I go back up to my table and I look for those values, 9, 10, 11, 12, adding those up, I get 0.931, 93.1% of students completed at least 1 year of high school. And then F, find the expected value of X. Explain what that result means. So that means I'm going to have to find the weighted average. In order to do that, I take each amount of years times its probability. If I go back up to the table, 4 years had a 0.01 probability. Then I'll go ahead and I'm going to add 5 years with 0.007, 6 years, 0.007, plus 7 years, 0.013, plus 8 years, which was 0.032, 9 years, 0.068, 10 years, 0.070, and then let's keep going, 11 years, 0.041, and they finished high school, meaning 0.752, 75% chance that they completed 12th grade. If I put all of those in my calculator, okay, exactly how it looks here, in the end I'm going to get the expected value. That will be 11.251. That's the expected years of school that a student will complete. So it could be expected that not everyone is going to complete them. On average, not every student will complete high school. This means the average 5th grader completes 11.25 years of school. Last page of the notes, if you flip on over. At the very top, there's a vocabulary word that we need to know. It's called the sampling distribution. The sampling distribution of a statistic tells us what values the statistic takes in repeated samples from that population and how often it takes those values. So we can often think of sampling distributions as the assigned probabilities for those values. Usually that's a lot. With real-world problems, these probabilities start to lose their jagged edges. With real-world problems, they start to build up and they start to form a smooth curve. We call those density curves. Now you can see with a dice, since there are limited options, specifically like with the games of craps, 2 through 12 is what your dice could add up to. We start to get this pyramid shape. If we have options, maybe not with just 12 results, but maybe 1,200 results, it starts to move more towards this fine curve. And we have dealt with this curve before. It's called the normal curve. And z-scores are going to be exceptionally important. So a couple of things that you have to remember about a normal curve. First thing, in the middle, we have x bar. That's the mean. If we go out we have 1, 2, 3, 1, 2, and 3 standard deviations. So this distance is S, and it goes out 3 below and 3 above. If you recall, we have 68% falls within the first two. Then here we have 95%, 68, 95, and then the last one is 99.7. So you have to remember those numbers as well, 68, 95, 99.7. Let's go ahead and let's use some of this for a real-world problem. They do this quite often. So 9, one way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. That way, if you know there's a certain amount of people and your survey doesn't have that amount, you're probably being biased against them or maybe for them if you have more of those than usual. So it says about 11% of American adults are black with a standard deviation of 0.8%. That is 0.08 as a decimal. Very important there. The proportion p hat, so that's a specific number that we found with our survey, for a simple random sample of 1,500 adults should therefore be close to 0.11. Okay, it should be close to this 11%. It's very unlikely that it's going to be exactly 11%, but it should be close. If it's not, then we're probably doing something wrong, and that's what we want to find out. If a national sample contains only 9.2% blacks, should we suspect that the sampling procedure is somehow underrepresenting them? Is it biased against African Americans? So what we're doing here is we're taking a larger amount of data and we're getting a smoother curve. This curve, though, still represents probability. Just like how with the Kraps curve, each bar right up here, that's a probability. It's just that we have more of them to choose from. So what do we need to know about this problem in order to get to our answer? First off, the equation that we have to remember with normal curves is this guy. Z equals x minus x bar over s. Z being the z-score. Remember those 3 z-scores here? X means the specific value that we found in our sample. And I think actually here that's the 9.2%. X bar is the 11%. That's the ideal. That's what the average is for the whole population. S, they will have to usually tell you, and I believe they tell us that the standard deviation is 0.008 as a decimal. So what happens if I put all of those things in? Where will I fall? What will my z-score be for this specific value? So I'll put 0.092 minus 0.11 over 0.008. If you plug that into your calculator, you get this, negative 2.25. So what is that? That is a z-score. Negative 2.25 means that I am below the middle of this graph. So if I count 1, and then 2, 2.25 is right over here. Now notice, it's actually already been shaded for us. 2.25 is pretty close to the number that they got because they used a little bit more precise data. We're just kind of estimating here a little bit. It's actually the 0.008 number is slightly off. I rounded that for you so it would make it easier. So what is the probability? How do I figure out this area? Well, if you recall, we have to use the big z-score table. Now, I won't make you guys take that out, but you might have to use that in the upcoming sections. Finding this area is actually the likelihood that it will occur. So if we are in this shaded part, that's the odds of it being less than 9.2% blacks. It doesn't look like there's very high odds. In fact, the probability, they say, is 0.0129. So the probability of less than 9.2% is equal to 0.0129. That's a 1.29% chance that on any given simple random sample of 1,500 adults, will have less than 9.2% blacks. That's not very likely. So because it is not very likely, the simple random sample method is probably biased. We'd want to switch methods, or we'd want to try to adjust it so that those people get represented fairly, probably close to this 11% that they actually make up in the population. So a couple of really big ideas there. First off, if we know it's going to be 11%, the number should be close. It very rarely will actually be 11% on the dot. Also, if we start getting more and more people, this jagged picture will become smoother and smoother and smoother. That's with more options. Again, the picture that we drew, that's called a probability distribution. Okay, and shading certain outcomes represents the probability of those things happening. I hope this helped you guys out a little bit. The rest of the day is going to be a work day for you guys to get some of the homework done. Tomorrow will also be a work day. If you have any questions, please email me. I hope things are going all right, and I will see you guys soon. Bye.